Pointers. You either love them or hate them, don't you? Well, it doesn't have to be that way. Today, I'm going to give you a brief introduction into pointers, give a hands-on example with linked lists, and go through some good programming practices to adopt when it comes to pointers. Don't worry, in this video, everything will be in layman terms, so I won't get too technical. Let's begin. First off, what is a pointer? Is this a pointer? Is this a pointer? Is this a pointer? Well, no. A pointer is just an address. It points to a location in memory where some data is stored. Think of memory as a bunch of cells, each of which has a value and an address. And a pointer is just a fancy name for an address, so a pointer is synonymous with an address. I don't have to explain the difference between an address and a value, right? So, what a pointer does is it simply points to a cell in memory. That's it, as simple as that. Now let's take a look at an example. Have you ever wondered why we need to declare variables with simple data types like integers and characters? Well, it wouldn't make sense to say int x in Python. In C, this is actually important. Python hides all of the memory allocation complexity, while in C, it is only partially hidden. So in this example, when you type int x, the compiler allocates a 4-byte cell of memory for the variable x and stores its value, which is 5, inside that cell. This is pretty straightforward so far, but it is important for you to understand pointers. The int operation here also makes sure that the compiler remembers where the variable x is stored, i.e. its address. In other words, with simple data types, you don't have to do much because variable declaration does everything for you. The same thing happens when you declare a character, for example, the only difference being that a 1-byte cell of memory is allocated. By the way, a very important thing to note is that pointers take up more space than regular data types. Here comes some programming advice. If you're mainly dealing with integers, for example, and memory is limited, it wouldn't make sense to always use pointers, which take up twice as much space. Just keep that in mind. Next, let's have a look at some code. Here, I wrote a very simple program that prints the size and the address of variables x and y. As you can see, the output of the program is consistent with the previous slide. Feel free to play around with this code as well. Now let's have a look at a more complex data type to see what happens behind the scenes. Let's say we create a custom data type called person that has a name represented as an array of 20 characters and age as an integer. If you're not familiar with the syntax, don't worry, just refer to this code. Let's declare a variable of type person called p1. When you compile the program, the compiler automatically allocates 20 bytes for the name and 4 bytes for the integer. This means that when you set the name of p1 to say Dave, you don't have to worry about allocating 20 bytes to accommodate the string. In other words, the compiler allocates size of struct person bytes. Size of is a handy built-in C operation that you can use to calculate the number of bytes a data type takes up in memory. Now let's consider the case when we declare a variable as a pointer to a certain data type. Let's say we declare a pointer to an integer x. Here's what happens behind the scenes. First, the compiler finds 4 bytes to store an integer. Why 4? Because we're declaring a pointer to an integer, so the compiler will expect for that pointer to point to a 4-byte cell. Once the compiler finds that 4-byte cell, it records the address of the first byte of that cell. It wouldn't make sense to record all the 4 addresses associated with each byte, so we just need one. Next step is to find 8 bytes to store the address of the space we just allocated and store that address in there. Please refer to the picture for an illustration. The compiler now knows that these cells are no longer vacant. The final step is to assign the address to x. Now let's have a look at some code. Here, we try 3 different operations, getting the value of x, the address of x, and the value at the address x points to. These are the 3 main operations associated with pointers. Again, first off, we are declaring a pointer to an integer called x. The value of x is the address of the newly allocated 4-byte space. That 4-byte space, by the way, currently contains gibberish because we didn't initialize our integer to anything yet, we just have a pointer. We'll talk about how to do that later. And indeed, our code confirms that x stores an address. Now let's have a look at the address of x itself. Please don't get confused here. X's value and x's address are 2 different things. Its value, again, is the address of the newly allocated 4-byte space for an integer. Its address, though, is a pointer to an integer. Do you get it? If not, it's fine. Just have a look at this diagram. The takeaway here is that the address of x and its value are two different things. The value can be an address. If you differentiate them properly, then you should be fine. Just don't get confused. The value is different from an address. Next, let's see what happens if we try to dereference x. Dereferencing sounds complicated, but it's actually very simple. Think of it as backtracking. We have x, which stores the address of the newly allocated space for an integer. If we dereference x, we follow the address it is storing, or in other words, it points to, and retrieve the value from that cell. In this case, since we have not yet stored any meaningful data in that space, it contains gibberish. If you try to read that value, your program will likely behave strangely. What is worse, though, is that the compiler doesn't detect this error, so if something goes wrong, you'll potentially need to spend hours to pinpoint the cause of the problem. Again, dereferencing is like backtracking. Value to address, value to address, value to address. That's it. The takeaway here is that it's good practice to always initialize pointers with values, even if it is null. When you assign null to that memory cell initially, the compiler will throw an error saying that dereferencing a null value is illegal, which is much better. Dereferencing uninitialized cells is dangerous and should never be done.